Okay, hello everyone. Welcome to the first episode of Happy Hour with Architects. I have chosen the topic of exploiting microarchitectural vulnerabilities as the first topic in this session. And the reason I have chosen it because it demonstrates that in today's world, computer architecture is not just about hardware. It's actually way more than that, and people actually have to have the expertise in both software and hardware to build the systems for the future. So let me introduce our guests today. So Daniel Gruss is an assistant professor at the Graz University of Technology. He was the key member which introduced the Spectre and Meltdown attacks, exploiting speculative execution in the software. And after that, he has done many more works in this direction. And his recent work on load value injection, I think that is giving him a celebrity status. Like there is a movie trailer just to promote that work. And if you have not watched that trailer, you should. So it takes a detailed and deep knowledge of architecture, microarchitecture, operating system, and more to actually demonstrate these attacks. And that is why he's the perfect guest today to talk about this topic.
Thank you for the kind introduction.
Thank you. Jon Masters, he's our second guest today, and he's the vice president of software at the recent chip building startup Nuvia. And before that, he was the chief ARM architect at Red Hat. A design principle Jon always talks about that he wants to make software boring. And I'm assuming that he's working very hard to make that happen at Nuvia. Jon deeply cares about hardware and he has a thorough knowledge of microarchitecture. And there aren't that many people who actually have these strongholds on both software and hardware. And that is why Jon is the perfect guest today to talk with Daniel and discuss the recent trends and the future of hardware security.
Thanks for the introduction. And it's also nice to be here for our little reunion of great people together. So thanks.
You're welcome. So I will actually would like to start with Jon, and I would like to know from both of you that how did you become interested in hardware security, like how that happened, and maybe some personal stories that what motivated to become interested in this topic.
Mm-hmm.
So you want to start with me? Okay.
Yes.
So what got me interested? Well, my journey into computer architecture was, and then architecture security as an extension of that was a long one. I started out as a computer scientist who only really focused on software. And then over a period of several decades, I had terrible buyer's remorse, and I realized I'd made a horrible mistake in my life. And so I taught myself progressively more about hardware, and then got very interested in computer architecture. Read the computer architecture books, and what I started to do actually was I started to use some of the online MOOC kind of courses to fill in the gaps in my knowledge. So one I recommend to people is any course by Oner Mutlu, but there's tons of other professors out there that put their content on YouTube. And if you're trying to fill in gaps in your knowledge, it's been great for me over the years, just going for a walk in the evenings and watching a lecture or 10. And so that journey happened in parallel with running Red Hat's ARM efforts, trying to get a new architecture kind of fully bootstrapped. And then progressively seeing more and more interesting research happening in the security space, and hearing mumblings in 2017 that some scary stuff might be going on. I think it was probably Anders' blog that started a lot of us worrying that there were things going, in the summer. We saw that and thought, oh, that's interesting. And towards the end of the year, I think I'd read Daniel's PhD and a bunch of other research, and progressively thought, uh-oh. And I finally met him after he'd shattered the world. So it's been a fun journey.
Yeah. Yeah, for me, I also have more of a software background. So I'm also a computer scientist, and I was not doing anything with security until basically my PhD. So even in my master's, I didn't focus much on security. It was a catalog, but my focus was more on the operating system level. So my master thesis was taking an educational operating system, which was running on x86, 32 bits, and I ported this to several architectures and made the code more beautiful so that it really can be called a multi-platform operating system. And then I started that's also a funny part of the story. I wanted to continue teaching because my main motivation in this is educating others with the things that I know and that I think are important that others learn them. And of course, part of this is that I learn all the time new things. Learning never stops. But the things that I know, I can teach the students very well. And so this was my main motivation. And I went to my then PhD advisor. I applied for a PhD position, and I went to him and said, well, basically, I want to stay at university because I enjoy teaching so much. And I already had the opportunity to teach a bit during my master's. And he was like, well, that's not the right motivation to start a PhD. A PhD is about research. And I'm like, yeah, don't worry, I'll be fine. I can do that. And then after some time, he decided, yeah, okay, we can try that. We tried that, and it worked well. I had some interesting research results. Also there, I mean, this is not just my work. For most of the works, there was a different person, not me, pushing the main work, doing the main work for the paper. And it's just me sitting in the background and saying like, oh yeah, this is interesting. Maybe focus a bit more on this or focus a bit more on that. But it's my role is very often more in the background, steering things a bit rather than doing the hands-on work. I did a lot of hands-on work during my PhD, of course, but by now it changed.
Yeah, that makes sense. I think that's the journey of all of us. Like, I don't get to do that much hands-on work anymore. And
although I would like to.
I became a vice president, so I'm trying to resist the abstraction that happens over time as you get less and less hands-on.
Yeah.
We were just talking about that. Most of the day is spent on answering emails.
Oh yes.
Emails and meetings, right? And I mean, I've been, we're dealing with a pandemic, so I won't make too much light of it, but obviously, I've been socially distant for years in some aspects of my life. So sitting at an email is something that I'm very used to being in front of the computer at home for long periods of time. But it is interesting when you have people sort of thinking, do we really need to have another meeting? Do we really need to do all those things? And you start to get this time being freed up, which is, it makes you wonder, how much of that did you actually need before? So,
yeah. So one question I have is, like, as an architect, like, speculation is just like a fundamental core of what we do. And given that it's like so much in like all the hardware it has so many layers of speculation, like so many hardware structures that we do not invalidate if there is any misspeculation. Like, what do you think that like how bad the situation is? Like, what's the current state, and how many other ways you see people would keep exploiting these vulnerabilities. So I will start with Daniel.
So from my perspective, I think it makes sense to distinguish two cases here. The one is where the processor truly speculates. The processor does not know what will happen in the future. So it makes a good guess based on things that happened in the past, for instance, makes a good guess, goes that direction, tries these things. And if the guess turns out to be correct, then perfect, then we won a lot of time. But in the other case, and those are the meltdown type attacks, there the processor deliberately does something that is wrong, and the processor could at this point in time already know and determine that this is not correct and this should not be done. But the problem is that because this is all not software where we can easily, I don't know, cancel a thread or something, but this is hardware where this is all hardwired in some pipeline. There, it's difficult to stop these things that are already ongoing and making them stop early enough, not pick up more data from other sources. So these two cases, I think we need to distinguish those. For the one where the processor truly speculates on what will happen in the future, I think this is really difficult because we can't, I mean, the past thousands of years have shown that humans can't really get any better at predicting the future. Maybe in some areas, but in most areas, or generically predicting the future, quite a difficult problem, and we won't solve it with in this instance either. I'm afraid. For the other part, where the processor does something that we know it shouldn't do, and the processor knows it shouldn't do, for those parts, I would say that's bug fixing, and we will get rid of those bugs over the next decades. And there will be new variants, and there will be new variants again. So this will evolve into more or less the equivalent that we also have in the software world, where we also have the same types of bugs showing up all the time again and again. And we will eliminate bug classes, but there will be new bug classes and some that we might not defeat. For instance, we have race conditions. On the software level, we still can't figure out how to get rid of all the race conditions properly. On the hardware, I mean, the hardware, everything runs in parallel. It's made for race conditions.
That won't work in marketing, you realize, if you start saying made for race conditions. That's probably not a positive marketing term. I think Daniel's right there about the different areas that we want to focus on. It's sort of it's design, it's correctness versus you know, other optimizations that you might perform. I mean, the meltdown type attacks are you know, kind of more egregious, right? I think what happened is a lot of designs in the past, they saved some flops, they saved some logic by saying, well, that is a dead speculative path that's never going to ever be architecturally visible, so I don't need to track it. And I think one of the things that you need to do if you're building a design is you need to, people call them different things. One sort of term I've heard across the industry is a kill chain, but basically what you need to do is you need to track bad path speculation that you're going to need to kill or unwind or undo or squash or, you know, whatever. And you need to actually go and really track everything that it did and make sure that you do undo. Well, you can't make certain things visible. We can talk more about that. But other stuff that you did microarchitecturally, you know, a lot of the papers we've seen over the past couple of years that Daniel's helped to explore this whole space and really come up with some real nice descriptions around transient execution and so on. A lot of it comes back to the idea of having these dead chains that are going to keep doing a little bit for a bit longer. And more recently, I think you've seen that with things like microcode assists, right? Where you're on some x86 processors, not only do you have these dead paths that are going to go away, but what's going to happen is this dead path is going to basically be replaced with stuffed UOPs that will go and be delivered from microcode. And so again, there was an optimization there to say, well, I really don't care about any of that, so I'll just let it kind of peter out at the tail end of the pipeline, and I'll stuff in the UOPs I wanted. But unfortunately, if you can observe any of it, you can do quite a lot of damage.
Yeah. You call it dead paths. We called it zombie loads because we cared more about the loads. But you're true. It's true. It's the that passes. It's the processor that does something that will never be needed in the future. Yeah.
Mm-hmm. And you actually waste energy doing that as well. One of the things that frustrates me from a lot of these designs is that computation is not free. So speculative computation that you then throw away, ideally what you would do is you would stop at the earliest point in time and not have the processor spend any cycles more than. So not only is it a security thing or not correctness, because you can argue about whether speculation is architectural correctness or not, but it's just inefficient. You really want to I think if anyone's designing a processor, I mean, it's easy for me to say we're building something from scratch, so we can hopefully not make these mistakes. We'll make other mistakes, I'm sure. My colleagues are not listening, but but that's what happens, right? But you learn from it. But I hope when people go back and look, they look at just the efficiency as well.
Mm-hmm. This is something that I'm currently not seeing in the security community enough, and that I hope that we will see in the future. For many of the security patches, also around Spectre and Meltdown type attacks, we see estimates for the overheads, and efficiency is often neglected. And energy consumption even more so. What does it mean if my patch consumes 5% more CPU time? What does it mean if it consumes 5% more energy? What does that mean in energy consumption globally speaking?
That's a very good point. So I think the architects, people used to have this notion in our heads that invalidating stuff is expensive, and also sometimes the programs may use, like if I actually brought something from memory to cache, it's highly likely that it will be used sometime in the future. So why kick it out or why invalidate it? So I feel like there is no study which looks into this cost benefit analysis, that how much cost we will pay for the detection and the patches versus how much cost we will have just to make sure that as soon as we know that it has been it's going on the wrong path, let's just squash it. Yeah,
I also think the unrolling has the risk that someone that a sophisticated attacker could in parallel already observe the effect before they are unrolled, and this would also be a problem. We've seen that in several attacks in the past, especially with SMT hyperthreading. But in general, there might be ways to observe that also on non-SMT systems, non-hyperthreaded processors, because we have cross-core cache snoops and things like that.
That's right. You can't. Right. So when I'm saying you want to be careful about sort of killing bad path speculation, you can't just assume that you unwind it because as in you unwind cache effects. If you kill things at certain points in time, you can be okay. But there are certain points where you've had a UOP that's gone past a certain point, and it's now visible in terms of the memory subsystem or something, and then you've got bigger issues on your hands. So yes, it's a holistic view, right? So I think you've done an amazing job at sort of, what did you have, 4 different categories of transient execution attacks.
Yeah.
And I'm sure you'll describe that a bit more in a minute, but I think there's another level beyond that in terms of research over the next few years around what's the guidance for mitigating.
This was very, very interesting. This was a collaboration with Jo van Bulk from KU Leuven on the load value injection paper. And when
Book of Genius, by the way, beautiful.
Yes. it was Jo's idea. Moritz had the same idea from our group, but he didn't, and we didn't realize the significance. Jo had this idea independently and recognized how significant it is. And when we thought about how to present these attacks, we came up with this table with the 4 squares, where the first square is the branch prediction attacks, where you perform a branch and based on where the branch goes, determine what branch directions the other program, the victim program, took. And those were the old branch side channels, real side channels. And Spectre took this and turned it around. The leakage from the leakage of past branching decisions, turned it around into injecting false branch predictions into a victim domain. And then the victim goes all into the wrong directions.
Inception.
Now, Meltdown, yes, a bit like it. And then Meltdown was a bit different again. Meltdown actually leaks information. We don't really have a victim domain in a Meltdown attack. We just try something, we get the data, and we shouldn't get the data, and it's just leakage. I wouldn't call it a side channel attack because we actually get the data right away. So there's no inferring what could be the actual secret like in a traditional side channel attack, but it's really just getting the data, just an information disclosure attack. Now for Meltdown, again, this is leakage, and you can turn this around and then you get load value injection, because every time a load falls or is assisted or is aborted for any other reason, the processor still continues a bit, runs a bit into the dead path, and there you can lead it the wrong direction with the values that you inject there. And this is this really helped a lot. When we started research in this direction, I remember very well, I think this is on record on many occasions, where I said, like, Spectre will haunt us for many years and we will discover many new variants of that. And Meltdown, that's the big problem. It's a problem for now, but now that we patched it, it's also fine again. And of course, this was wrong, as we know now, because just 8 months later, there was Foreshadow, or L1TF, which was in some sense even worse than Meltdown. And then year after that, we had zombie load, real MDS attacks. Yeah, and now LVI. So on the Meltdown side, we've seen many, many more variants. And on the Spectre side, it pretty much stayed the same, which doesn't mean that the Spectre side is less problematic. I think the Spectre side is much more difficult to solve because you can't just solve it on a software layer. You can't just solve it on a hardware layer to a degree that where everyone is happy. For Meltdown, it's totally, I would say it's trivial to solve all the Meltdown type problems on the hardware level once you know them. Yeah. You have to spend a few more gates, but it's trivial to solve them, I would argue. It's a bit of engineering.
I used to joke, and I said this in a different podcast that I was in, that I forget the page number. It's in Appendix B of Computer Architecture. I think it was page 46, or I could be slightly off. But there's a section in Computer Architecture where Patterson and Hennessy say, you really want to make sure you do the security check in parallel when you're doing your page table walk and your TLB lookup and so on, because you could end up with a horrifying security issue. Basically, paraphrasing what they said. But that was present there since their first edition. So that was however many years that's been written in an appendix. And I did buy a copy of that book as a holiday present in December of 2017, right before you came out. And I gift wrapped it for a company in a certain part of the world. I didn't send it to them. I resisted. But I had it ready to go, and then I was like, "Nah, that's a bit too mean." Because the thing is, anyone could make. I mean, a lot of people did make that mistake, right? It wasn't like there was one company in particular that got, hit with it. But I actually thought when you came out with the stuff that, with Meltdown in particular, that what would happen would be that cell phones would be in the news, because more people have a phone these days that they care about with their personal data than their laptop or their server. And it was interesting that it turned into a big focus on just different. It was just different than I thought it was.
Yeah. I also was not really happy with that, because in the media coverage it was all turned into an Intel only issue, and that was clearly not the case. We already made that clear from the beginning that other vendors are affected as well. But this is something that you don't really control. We had good experiences with disclosures and bad experiences with disclosures. I wouldn't say that Meltdown and Spectre were particularly bad. Not everything goes exactly as you wanted, but overall, the message that we wanted to communicate came across. This is a significant issue. It is relevant for everyone to patch their systems now. There are patches, patch your systems now. For other cases, usually this entire media thing, like talking to journalists and showing them a website draft, giving them a short text that explains the issue in more simple words, giving them the paper ahead of time. This is something that we didn't do when we were just working on regular side channel attacks. I wrote many papers in that area, and usually this would not be anything that journalists would care too much about, because yes, then we get half of the bits of a crypto key, and what does that mean after like 3 hours of attack? Like, this sounds more academic, but with this we have to basically tell the journalists ahead of time what they can expect here. We didn't do that recently for one paper that was the AMD takeaway paper. We attacked the AMD way predictor. Really interesting microarchitectural element, and we hoped that we would find something really interesting there. We did find a side channel which was interesting. We were thinking that there could be something more depending on the design. Luckily for AMD, they didn't design it that bad. The cache weight predictor is actually not. I in some discussions I even said it shouldn't be called a predictor, because it's not really doing anything predictive, but it's more like a cache.
It's lighting up the way ahead of time, right? Because they've got an L1 that's larger than 32K.
Actually, I'm not sure they. So I think they have that also for designs where they have a L1 that is just 32K, but it still gives you some performance benefit. If you have an L1 miss, I think it was the case where you have an L1 miss, you can send the right request to L2 earlier. So you would see a difference in the latency if it's in the wave predictor and in L2, or not in the wave predictor and in L2, things like that. So anyway, this was a side channel and not a particularly strong side channel. And we disclosed this to AMD, and also the response from AMD was not that long, and it was clear to us that they wouldn't ask for or we expected that they wouldn't ask for an embargo, because this was not really a significant issue. And also we didn't hear anything back from them. So we just put this online. We didn't contact any journalists, no media coverage, no media work, anything. So this went public, and journalists pick it up, and they are like, oh, this is the next Meltdown thing, and now it's AMD, and it's super big, and everything's broken on AMD. And of course, this was not correct.
Right.
But what do you do then? I mean, we we couldn't make this stop at this point anymore. If you choose from the beginning to not work with the media, then you just lose the opportunity to work with the media. That's it. So this is a lesson that we learned there. We always have to brief the media so that we do not lose this opportunity.
Controlling the story, I think that's what you're saying, that otherwise the
Yes,
story is
yes.
just out of your hands.
Yes. Yeah, it's important because these for AMD this caused a lot of stress, I guess, and for a lot of people that were either working with AMD machines and not sure what they should do now, because there's also no patch for this. This is a side channel. Caches are inherently side channels because you can probe what is cached and what is not cached. So there won't be any patches for these kinds of issues if we discover a generic side channel. So also anyone who was using an AMD CPU then was wondering, should I install a patch? Where's the patch? There's no patch. So this is quite bad because yeah, we didn't brief the media in which way they can report about this issue.
I think it's you know, on balance, having sort of observed your work and other researchers for the last few years, I think you've done a great job with it. I mean, in some cases, the media, because you're dealing with a topic, and we said this earlier, right? That a lot of software folks are not really very attuned to the underlying hardware microarchitecture implementation. That's certainly true for journalists. I mean, there's some that I talk to, I regularly interact with on Twitter, who are very, very well informed
Yes.
on balance and really do understand. And so, you know, I won't call out particular names, but I think we know who we're talking about. There's some that are really, really good, and then there's some that it's not malicious. It's just you could say, you know, here's a toaster that's doing.
They try their best.
Yeah, they try their best, but it's not. It's like it'd be like me. You know, I have a book on how the engine in my car works. Have I ever read it? No. Do I wish I would? Yes. Right. I'd like to know how the engine in my car works. I'm not that concerned right now. I haven't bothered, and I think that's true with a lot of you know, they'd love to know this, but they don't, and this all kind of crept up on them over the last few years, and so they're just trying, and it's hard to know, is this a big deal or is this just you know, some minor thing that happened? And
I think this is also important because it's not really so we have to think about what is their job and what is our job. This is also something that I discussed with my students because very often we are like, no, we don't want to approach journalists for this issue because it's not significant enough. We don't want to approach journalists or have a website or anything for vulnerabilities that are mainly of academic interest. If they are not relevant for the broad public, then we don't want to have this, right? Because we don't want to water down our message when it's important. Now, the problem is that if we don't approach the journalists at all, then we don't even decide that anymore. And so we should always approach journalists and provide them with the information. This is what we learned. And the journalists will do their job and they will make the decision whether it's relevant for the general public or not. And I think this is the way that it should work.
I think on balance, you know, when Spectre Meltdown first happened, you know, being in a different role at the time in a big software organization, the thing there was that we didn't have you know, the bat phone to all the companies. We were scrambling, and everybody was, right? It's not just that one particular place that I was. It was the whole industry did not have those bat phones set up for, oh my goodness, everything's broken, we have to fix it. And in the last few years, that's really been fixed. So there are now the right sort of point-to-point contacts. And, you know, it's another thing. When I decided to move on and do something else in my life, it was thinking, you know, do we have all the right things in place? Yes, we do. There's you know, it's not just sort of, I know so-and-so, therefore we talk. It's a bit more structured now that people do have ways to reach each other. And so, you know, I actually think things went pretty well. I mean, you know, this was literally the first time that anything that awful had really ever arisen. And Yes, it was a little bit sort of sensationalized by the media, but it was pretty bad as well. So, and you know,
in hindsight, I don't think it was sensationalized too much, because it was very important that everyone gets the message, update your system now. And still we got a lot of questions from various people like, should I really install the updates now? Is it really necessary? Like, yes, it is necessary, because Meltdown was, if you have a Windows XP 32-bit system running now somewhere and it's connected to the internet, and you would access a website with that system, that website could, as of today, still mount a Meltdown attack and read any data on your entire system. So
I agree, Daniel. There was with that, and I think it was, you know, it was so awful that we used to say two things actually on the other side of that. We used to say, well, you know, Spectre variant 2 and Spectre variant 1 were very significant as well, but without Meltdown, the whole set probably wouldn't have gotten anything like that. You know, you had something that was so egregious that it drew attention, right? And then the other thing that was, I agree with you that everyone should patch and update their machines because it's so awful. You know, JavaScript attacks dumping your memory is pretty awful, any way you look at it. But the other thing that was kind of, I won't say funny, but the other thing that was interesting was people went a little bit too far the other way. And so what happened was you'd get people saying, I want fixes for this on an unsupported software release from years ago. That's what XP's reminded me of. And you would tell them, well, okay, but there's also all these other critical CVEs that have happened in the past couple of years that you're vulnerable to. And they would, paraphrasing, they would say, yeah, but that's not the thing we have to care about today because we have to care about this thing. So you'd be like, all right, well, we can fix that. But you realize that you're not getting fixes for all the other things that are not supported anymore. And you're running software that no one's releasing patches for. Do you realize that you're asking for a fix for something that has other things in it that someone could be using to attack you? So it was very interesting to see the psyche as well, where people sort of zoom into one thing and you have to sort of remind them that there's a whole world of other stuff that they probably got you with as well, right?
Yeah.
So we touched a bit on like we have to educate or we have to educate our journalists, but I think here you are actually at something very important, that we also have to educate our software developers and also people who are building the hardware, right? I think like in both direction, people have to have these new type of mentality that whatever worked before will not work now. So in terms of that, like, how do you think, like, how should the mindset should change? And Daniel also mentioned about data races and how we write our software and how to avoid data races and the whole thing. That also required a lot of training and education, right? Like even now, many people do not understand it. So what's your thoughts on that? Yeah.
So I find it really interesting that you mentioned the mindset here, because this is something that I often, so I noticed that several times when talking to computer architects. I'm not a computer architect, and my computer science experience, I shifted very much into security because my mindset was prepared for that. When I was a teenager, I played a bit around with modifying Game Boy ROMs to my liking, and doing all kinds of things that with software, or mainly with software that the software was not supposed to be doing. So I always had this idea, like, what can I do that I'm not supposed to do with this? And this is I would say, one of the main things that you need in security, and that the architecture community should probably pick up more. I see a lot of papers from the architecture community on security topics where I can quite easily figure out what the malicious actor would do to bypass it. So this mindset of, if I'm a malicious actor, what would I do? This is very important in the security community, and I think this is a noticeable divide between the architecture community and the security community, and we need to close that gap. I don't know whether it's possible and how far it's possible, but that would be great.
I think there's, you know, I don't want to sound like I'm marketing the company that I joined. I mean, I love being at a startup, and I thought I would never leave my old job because I still love Red Hat very much. But it's just been someone made me an offer in the end I could not say no to, which was to go and learn the things that I always wanted to. So I used to say I play a computer architect on TV, and I still do. But I increasingly I'm learning the sorts of things that I wanted to learn about how it really works underneath. And I have been pushing for this sort of holistic view of things. And these guys, I think get it. We'll see how it goes over time. But there is a sense of across the industry, not just in the place that I'm at, but I'm hearing it from others, that there is a renaissance in terms of interest in looking not just at performance, but also the security trade-offs. So every new feature, you need to now look at it from the point of view of, okay, that buys me performance, but how does it get broken? And one thing I'd like to see is, and we can talk more about hardware, software, co-design, but I'd like to see also more relationships. I always said that when I changed my job, I was planning to keep talking to Daniel, and I do, and I plan to push the hardware industry from the inside to collaborate with researchers in academia, because I think it's very important to pick holes in something, right? Because what Daniel at Gruss and other institutions are doing are not saying, here's a horrifying hole, and oh goodness, that's terrible. If only Daniel wouldn't do that, right? The bad guys are going to find these problems. All you're doing is highlighting that there is a problem there. And if you want to build a design today, everybody who's building something is targeting sort of hyperscalers and big homogeneous surfaces where you might have millions of machines that are all the same. Right? If you're designing something, this needs to be the number one focus. I mean, performance is important, but if you put something out there and you've got more than 1 million, I mean, even in a phone or a laptop or something, if you've got millions of them that are all identical, it's great for an attacker just to go and find something, and then they've instantly taken down very large numbers of machines.
The problem that we have there, though, is that it's difficult to assess how relevant different security vulnerabilities are. If I'm talking about a generic cache timing side channel, we don't want to fix them in hardware. We don't really, maybe we want to make them more difficult to mount, but really stopping them from being possible, no, because we want the performance benefit. In general,
same as you
also,
won't fix Spectre variant 1, right? You won't fix conditional branch predictors. You just won't.
So the general question in security is, how do we measure security? This is a problem that has been ongoing, and I'm not sure if we are going to solve it or when we are going to solve it. But measuring security would be really great. If you think about safety, you can measure safety. Like, what is the chance that I survive an accident? You can measure safety. Maybe the measurement, or you can estimate it, right? You can make an estimate, and maybe it's not very precise, but for security, we are very far from things like that. And therefore, it's difficult to convince users and also maybe also within companies to convince people to invest into security and to assess how important security is.
I think also designing for mitigation is very important as well. So, in addition to having sort of the, there's different safety bodies. There's the National Highway Transport Safety Administration. I forget the exact acronym in the US, but they do the crash test dummy tests, and they're similar in Europe.
Yeah.
And that's sort of what you're alluding to, right? Is that this microarchitecture has been crash tested and rated with this number and all that. But I think also you want to design something so that mitigation is not always fail deadly, right? Like it's not always fail with the most egregious loss in performance. So there's a need to look at things and say, what knobs and levers can I put in there that later on when a problem is found, the cost is not the most horrific.
Yes, we are working in projects in that direction to think about what knobs should be there. So the question there is, how can you do that? We had some cases where we were quite lucky. For instance, with the Kaiser patch, KBTI patch, we designed that, and it had this overhead which was too high. And then later on, not us, but I think Intel, while making these patches really work, because ours was just a prototype which worked randomly from time to time. And they decided that they will merge the PCID patches.
The address space IDs that they had,
Yes, and this basically solved a large part of the problem, the performance reduction, because now you could keep those TLB entries across context switches because they are tagged with different PCIDs.
I pushed people like ARM later to add what you now see in ARM. You now see a context ID added as basically a sub-address space ID, because you get this with managed runtime environments like Java, right? You're running your sandbox there, and we've seen attacks there that you're running a malicious workload, and okay, if you can only attack the sandbox, but you might get some very interesting data out of that. So you actually want to divide it down to sub-address space IDs as well, I think.
One question I have to John is, like, do you see this change in mindset in the new company compared to maybe Intel? Like they have been doing it for decades, and they have a different mindset than someone who is just starting, right?
So all right. So I'm gonna say one thing in Intel's defense. I promised, by the way, a couple of weeks ago, we had we're in a pandemic right now. I've promised to be nice to Intel, more or less, until the world returns to normal. But it's very easy to pick on them because they're the big fish, right? So I will preface everything I'm saying with, there's a lot of very nice people at Intel. I like to joke on Twitter. I like to be outside their building and do the jingle and have fun. And hi, all the Intel folks. We love all of you very much. So they're a big target. It's very easy to pick on. I do think, though, that I think they're getting this as well. People there that I still keep in touch with, they understand the changing mindset. In my old life, I got to give a talk at one of their internal conferences about how I thought things should go, and they really were showing signs of listening. So I thought that was good. In the new place, look, I joke that I said no for about 6 months, and I finally said yes when they basically every sort of, they wore me down, right? It was just because I had said, well, I want to do everything sort of with no barriers, and I want to do it this way, and they're like, okay, fine. I'm like, oh man, okay, I've run out of reasons to say no, right? So they do understand the folk, how this needs to be done, and since I joined, what I've done is I've sort of gone through with lots of people, lots of different security, potential side channels, and what would happen here and what would happen there. And it's very easy to focus on the past. And the problem is, you could design something that was very robust to existing attack. I mean, you should, right? You should obviously design something. And I tell everybody out there, look, Google has a repository on GitHub called SafeSide, right? I'm going to give a plug to Chandler and co. Thank you for creating this, Chandler Carruth at Google and others for having this repo. It's called SafeSide. It has all kinds of little synthetic tests. If you're building something and you haven't tested all of those to make sure that you're not exposed, then you've done something wrong, because that's free, it's there. Why the heck are you not running it? But all that does is it tells you about the past and tells you about attacks that have already been published. What you need to do is you need to look at new designs, and you need to think about, again, how could this be exploited? How can you design to make it mitigated? How can you apply the kinds of thinking that the researchers have? I don't claim to have all the answers. I do like what I see in terms of people's perspective, and there's a religious focus on performance, but there's also a strong understanding that it has to be done in the context that you want to put these machines into these homogeneous environments and be able to deal with the consequences. So I like what I see. I don't think Nuvia has a monopoly on getting that right. I think that everybody is starting to really understand that there needs to be a different way of approaching this stuff.
So the other side, sorry, go ahead.
Yeah, I'm really hoping that the industry will make this change, but the mindset thing is something that is really worrying me, because I've talked to several occasions. I've talked to architects, and I always had the problem that the mindset that we find a lot among security researchers is much more focused on how can I find my way around this barrier. And this is something I'm not sure whether it's part of what you focus on. If you focus your mind on optimizing something for efficiency, for performance, and if you focus your mind on finding flaws in a system, I don't know whether one person can be the best at both at the same time.
Yeah, maybe no, right? Yeah, maybe no.
I think we've seen over the past couple of years that Intel's done a lot of recruiting around the security community, right? And that has both positives and negatives. You want to make sure that people feel very free to still publish and engage, and not under the corporate thumb. But let's take it from a positive perspective for a second. Let's just say that I think a lot of companies, there is a strong need to build out capabilities here and have dedicated resources that go and audit designs and look for problems from an attacker's perspective, not just from a architect trying to get every ounce of performance out of something.
Yeah. The complexity, though, if you optimize for performance, and that's your main focus, that's something that works, right? That's how the industry is already established. Finding security problems brings in another dimension of complexity here, not in terms of design complexity, but in terms of how do I find the problem. If I search for, if I have an optimization problem and I want to optimize it for performance, that's one dimension. But if I want to find all the security problems in a product, that's something much broader. And I think even if the companies will invest here a lot themselves, I don't think we will reach a point where we can say, okay, we don't have any security problems because we had enough investment into the security people in our company and they found all the problems.
No,
so it will always require research from external third parties that search for problems as well. And even then, we won't find everything.
I think all you can do is design robustly so that you can mitigate in less disastrous ways. You know, designs have always had defeaturing bits, and they call them chicken bits in the industry, right? So you chicken out of some fancy whiz-bang feature that you built, but it used to be that the number of chicken bits were proportionate to the complexity of some whiz-bang new feature because you're a bit worried that you've got it right. And now it's sort of, you know, some of those bits might be more motivated by having that fine-grained back-off in performance. If you have to turn something off, maybe you don't turn it off completely. Maybe you start to turn off little pieces of things.
Yes. Which is a very organic way of approaching things, because that's how biologic organisms also function, right? If I have a problem with the hand, some disease, and it would spread, and I can, depending on the disease, depending on the infection, chopping it off solves the problem, because it's a line of defense, right?
Yeah.
It's a line of defense, and probably it impairs me less than letting the disease spread through my entire body. And that's
Doctor, it hurts when I add numbers together, so let's not add them together anymore.
I still have another hand.
I love you.
Nothing can stop
No,
Daniel.
it's actually, I mean, the solution, what are we doing against all those hyperthreading side channels? We are disabling hyperthreading. Let's work with one hand.
Yeah.
Yeah. Yeah, I think that is why this conversation, like, I also think that most probably one person cannot be security expert and also microarchitectural expert. So that's why we need this conversation, that people talk to each other and understand that how the other person thinks, and take advantage of these two different types of mindsets.
Yeah. I think it needs a constant exchange, because picking up, I couldn't, so even if I talk to an engineer who is really good at optimizing things and coming up with new ideas how to optimize things, even if I would see that, probably it would be very difficult for me to pick up that mindset and pick up the way of thinking so that I can do the same. But if I just talk to this person, I will be able to understand his ideas or her ideas, and vice versa. If I explain how I would bypass some isolation mechanism, then they will easily understand that.
I apply it in hiring discussions too. I mean, I'm not looking to see somebody explain to me every aspect of a out of order execution, right? But I definitely will ask everyone that I hire in the software team that I'm building questions around out of order execution, and I will ask them. I like to ask questions about memory consistency and coherency and all these kinds of things too, because I want to see that they understand, at least at enough of a level, what's going on underneath. You don't have to have all the fidelity there. That's not the important thing. The important thing is to understand that the computer that you think you have from a software perspective is not what you do have. And I'd like to see more happen there with education too.
If we have time for a short detour, we have these discussions at our university, and I think they are around the planet at all the universities, like what language and what techniques should we teach to our students? And there are many people who think, well, basically we don't have to teach the students C anymore. They don't need to learn C or assembly or any of this stuff. They should write stuff in, I don't know, Node.js, maybe as a low-level language, and the other thing will be just click and point, or I don't know. So the question is, what do you think there? I think it's important to learn C, and I'm very happy that we start in our first semester undergraduate studies with C programming, because you learn exactly that. You learn what happens underneath.
Samira, what do you think?
So, so this semester I'm teaching undergrad computer architecture. And because it's a computer science department, my assignments, they are not RTL based. So they are learning about branch prediction and processor, single cycle, multi-cycle, multi-stage, but the assignments are all in C. And to my mind, I was like, yeah, I'm not asking them to do RTL, it's in C, so it should be pretty easy. And then later I hear that many of them never worked on C. So to me, I feel that we should rethink which languages we teach our students. And I would like to hear John's opinion that in real life, how much they will use Python versus some other language.
Oh yeah.
I think it depends where you are. I mean, in my old life in Red Hat is you know, a lot of the application software is actually, yeah, it's C and C++, but also very heavily Python. Most of the utilities and graphical software you're seeing is being written in higher and higher level stuff. I think if you're looking at that sort of modern world of you know, containerized microservices and all the things people are deploying, web stacks and so on, then teaching Node.js and Python is a reasonable thing to do if you're going to be working on web stacks. I would argue if you're studying computer science that you ought to be doing, I don't want to sound too arrogant here because I'm not trying to be that person. But I think that I think there's more to it, right, than just getting a job and being a web programmer. You want to learn a bit more. I actually don't think the first language that you have matters. I think, for example, you could have an undergraduate computer science education that begins with, you know, personally, I would say, you know, if I was teaching one, okay, I would start with C, but say you start with Java, say you start with Python. It doesn't actually matter as much. What you should do, though, is you should immediately or pretty early on take that code and say, okay, you wrote this in Python, but what actually happened? Look at your computer. You're going to see these PYC and PYO files where the Python runtime has taken this and it's optimized it and jittered it, and it's done very interesting stuff underneath. And then, you know, even if you look at, even if PHP was the first language you learned, right? You look at Facebook. They have this thing called HHVM, hip hop, that takes PHP code and jits it, right? So what you could do is you could start with something that's very abstract, that someone, you know, that's a scripting language, and you could say, well, here's the translation that happens underneath, and you could walk them down through it, and you could say, and then this is what actually happens in the architecture underneath, and you could map it back to all of these things. And I think that could be one way to do it too. But so the language you start with isn't as important as making sure that you go right down and have an understanding of what's happening underneath. And at least everybody graduates with some understanding that there's a lot of depth to it. Maybe not everybody becomes in the future an assembly expert. Everybody should have exposure to assembly. You know, and my ideal, you know, if I was creating a curriculum, the ideal that I see, and this is informed solely by my own interests, right? So I've got my own biases. But you know, I'm blessed right now that I get to spend in my life, I get to look at a mixture of, you know, software and also the RTL for things underneath that are actually running that software, right? And I think that there's an amazing amount of understanding that you can get if you look at both halves. So I would love to see, for example, curriculums built, and I know both of you have institutions that are looking at RISC-V as an example, but you know, building, you know, it's possible right now for someone to go and take a synthesizable RTL processor and with a reasonable amount of effort, not an infinite amount of effort, to take that, put it onto some kind of either a simulator, an emulator, or FPGA, whatever, and run a full OS and really see the top to bottom stuff I'm talking about. So it's not even like in the abstract, you know, run something on your laptop and it turns into assembly, and then who knows what happens after that, after you get these instructions. You actually could show them the whole stack. And I'd love it if every graduate had some idea of you know, what a flip-flop is, and you know, what, you know, even if you're a computer scientist, not a computer engineer, I would love it if they had some understanding. It'll probably be a long time before we get to that.
It's interesting because for a long time we focused on making sure that people can specialize into their sub areas, and now it's becoming more and more important to understand things across layers. And this is something that was not anticipated maybe like 10, 15 years ago.
it's great for my ADHD, right? So I have a huge problem. I mean, I have a huge problem in my life that I can't use a piece of technology unless I have some idea how it works, and it becomes horrifyingly debilitating in many parts of your life. But in other areas, it's great. You're like, oh yeah, okay, well I really want to know how that works. So that's very convenient for me. But I think the other part of it is that we have this sort of end of, I'll talk about Moore's law being dead, right? I have to say it at least once, right? So the simple wins that we've had are going away. And since that's happening, software is going to matter more. I mean, you look at this talk that John Hennessy gives, right? Very often, he walks through the relative amount of performance wins you get taking some code that you wrote in Python, and then just switching it to C, and then optimizing it, and then hand tuning it using some kind of well, firstly using intrinsics, then hand tuning it, and so on and so on and so on. And he ends up getting from something that's 50,000 times slower, he ends up getting all these wins. And by the time he's done, it says, okay, so just by changing the software, you made it 50,000 times better performing. And people complain when processors are only getting 10%, 15% faster every year. And he's saying, yes, but look where the real area that you could get the performance win is, right? If you had a processor that was even twice as fast, or even, you're not going to get a processor that's 50,000 times faster, right? So maybe one of the places to really look at is, are we doing the most sensible things with our software? And I would agree with him and say we're probably not.
So maybe we need, because this also translates into energy consumption, maybe we need some CO2 footprint for software as well. Like, you're running this Python script nonstop on your server, this causes this much CO2 emissions.
Yeah.
And then you have some incentive to replace it with something more efficient. I don't know.
Yeah, I read somewhere that just training the deep neural networks for some papers takes so much carbon footprint they have that it's just unimaginable. 3 years of the same amount which a car will emit in 3 years, something like that.
Yeah,
that's terrible.
So John did mention Moore's law, which I was trying to see if we mention it or not.
Okay.
It's required.
So at the end of our discussion, I will give you some keywords, some really popular keywords, and I will just give me something which comes to your mind, like in a word or in a sentence. So first one is blockchain.
Oh, horrifying. So the first word that comes to mind is horrifying.
Well, the second thing that comes to mind is Git is really a great tool.
It's like, so okay, I'm going to be nice to IBM and Red Hat. I love them. I left, but I still love the company. They're great, right? But every time I would look at those IBM commercials where I would see them talking about quantum computing and blockchain, and I used to make jokes about having a quantum blockchain product, people would say, wait, really? No, not really. No, that's a joke, right? But anytime you have a strategy as a company that involves the words quantum and blockchain, something is wrong. Those are not strategies. Those are technologies that might be interesting, but they're not strategic. Like blockchain is not blockchain is something that you might be able to leverage and use. But it isn't something that it's just a tool. It's like saying wheel. Okay, wheels are interesting, but they're not strategic wheels.
Okay, second one, neural networks.
Daniel?
Statistics are really powerful in getting the essence out of a lot of data. And machine learning and neural networks, as I see them as applications in statistics, Yeah, they are quite powerful. The question is how much time you want to invest into analyzing the data and whether that is justified.
So
As
we
we just
learned
said,
about,
the carbon footprint can be quite bad.
I mean, in school, you know, for the last several decades, anyone studying computer science has learned a little bit about perceptrons, right, as a very basic form of
Yes, yes,
neural network.
yeah.
And so, you know, when you get processors that come to market that have a perceptron-based branch predictor, I'm picking on one company, I won't say their name, we all know who it is, and they say, oh, my machine learning branch predictor. No, it's you know, it's like machine learning in general. It's an interesting concept. It's very useful, but there's some great memes out there about replacing your machine learning whiz bang thing with a simple loop and conditions and so on and if statements, and it's overused for what it is.
Hard one, x86.
Daniel, do you want to start? And then I've got some thoughts.
I grew up with x86, and I'm emotionally attached to it. So I really feel home with x86, but I do see that it introduces more challenges than necessary, and that's maybe not good for security.
I want it to die. It's an architecture that is I also grew up, well, that's not true. I grew up with yes, sort of. I grew up with the BBC, and then I remember my father when I was you know, maybe 10 or something, ripping it away and giving me this PC and saying, you must learn this, and it was a 386, and if you know, if Diane Bryant ever watches this, thank you for working on that project. I actually really liked the 386. It was a great one. But x86 is long in the tooth, and this is not me being an ARM fanboy. It's just kind of sad that you know, somebody needs to take a sledgehammer to all these architectures that are beyond a certain point in time and say which parts of it matter, right? You could actually redeem x86, but what you need to do is you need to go through it and say, how much of this do we even care about anymore? I mean,
yes.
There's so many features in there. I mean, segmentation still lives on some level, and then you know, when you're trying to prove correctness, there's just so many little areas there where it's such an amorphous surface. And if somebody were to go through it and just play whack-a-mole and really remove all of the gunk that you don't need anymore, you could actually make, you know, because fundamentally every processor is doing the same thing anyway. It's taking this, you know, x86 or ARM or RISC-V or whatever, and it's turning it into a little data flow machine. And it doesn't really matter what the ISA is, but you know, ARM is well and truly on the path to adding so much complexity that it's going to be in trouble one day. RISC-V is coming along saying, "Oh, we've got the answer to everything." Yeah, well, no, they're just newer, and they'll have the same. You know, someone needs to have a process to deprecate parts of architectures, and I don't see that happening, which is kind of sad, because you could do it, especially in the cloud. You could say, well, how many workloads are you running where you really care about real mode? Really? Real mode? Really?
Yeah. We need a mechanism to fade out features. It's not there anymore in the next version. Yeah.
It might be possible in cloud, but have you seen that news that like CDC is looking for COBOL programmers because they're running all these COBOL applications? So like softwares don't die. So maybe there are something like, I think that there is a fear that if they fade out some of the instructions, some of the functionalities, they may lose some customer.
Okay, so I'm going to rant one more thing on that. So there's also this thing, this you know, I've got my beefs with Intel, just for various reasons. But there's lots of nice people at Intel, and they did. And x86 is it's amazing how it's kind of like Z architecture, right? The mainframe, you know, if there is a nuclear war, the cockroaches and the mainframes will be the only things left, right? They will just survive because that's what they do, right? And Intel x86 has survived for so long. It's amazingly resilient in that sense. But one of the problems we have in architecture is, so Intel and AMD add new things to their architecture, and they patent particular instructions. ARM takes a different approach. They use copyright to enforce their ownership of. They also have patents, but basically they copyright the ISA, right? And so, but neither is a perfect way of doing it. And so some of these companies need to just be realistic and honest about why they do things too. If you're adding instructions and the sole reason to do it is to keep alive your ownership of the architecture, there's got to be a better way. And the other thing I would love to see happen with x86 is I would love to see some neutral body formed where, you know, maybe Intel has 75% ownership over it. That's fine, you know, or 90%, and AMD gets 10%, and rest get 1%, whatever, you know, make the math work. But some way of making that architecture something that isn't just about adding new features over time to keep to own it, and instead have a neutral place that owns it, so that we can get away from adding all of these gratuitous features and even remove them. That'd be great.
Yeah, that sounds great. But how would RISC-V play into this model? How do you see it?
I love RISC-V. It's a great educational. It's going to give everybody competitive pressure. The one challenge is that you get these people that are very interested in blockchain. They're not always the same people that are very overly obsessed with RISC-V. They're different people, but they have the same kind of zeal about it, right? It's like just because you have an open ISA doesn't mean you've now solved every problem. Fundamentally, the problem you have with making a processor is it's really expensive. It's hundreds of millions of dollars to make a new processor from scratch. And so, you know, just saying I now have RISC-V isn't going to really solve for the problem that hardware isn't software, right? If I take a design and I open it and I give it to everybody, how do I return on investment the hundreds of millions of dollars that have been spent? So there are ways to solve that, but they require very creative sort of analysis. You know, I would love to see some rich billionaire say, "Here's $10 billion. Let's make all this problem go away." But until we get to that point, it's very tough. Daniel, you want to?
And open sourcing is also not a security strategy. If you just open source your software, that doesn't change anything about the software security. If you open source your hardware, that doesn't change anything about the hardware security. If you need to build in security by design, you need to think about how to introduce security mechanisms. Sure, you will find bugs from internal research. You will find bugs if you open source it. From external research, even if you don't open source it, you find them apparently. But it doesn't necessarily make it a better product. And I'm really afraid that the RISC-V community will focus way too much on the performance and efficiency, and not on security, and will end up with the same trade-offs that other companies have already made before. Or other architectures.
Yeah, I guess we should try to end with a positive note. And
you thought about Moore's law somewhere.
So I was thinking about bringing up Moore's law as the last topic. So let's end with that. Like Moore's law, very short summary of what you think.
What do you think, Daniel?
We've been several times there that people thought it doesn't continue. It's not the first time that we are there now. And so far it always came back. Let's see what happens this time. But I agree. It looks like it might not continue to be true for much longer.
John?
I think it's dead, and I'm actually very happy that it's dead. because what we had the years and years of our lives where software kind of was off the hook as far as having to really worry. I mean, it wasn't really off the hook, was it? When you think about what Hennessy's been talking about in terms of the 50,000 times, all these wins. But we got faster and faster chips every year just from better manufacturing. So we didn't really have to worry about the software as much because we could kind of kid ourselves that the hardware was just getting faster underneath. But by the way, it's amazing when you see some of these speculative execution attacks and so on. You think about the brilliance that went into some of these performance optimizations just to get us these faster chips every year, right?
Yeah.
But with the death of Moore's law, it actually gives us a lot of interesting opportunities, I think, to focus in the other areas, right? It's not just manufacturing. Now you have to have interesting architecture innovation, but also interesting software innovation. And so it's actually a fabulous opportunity. It's a great equalizer, right? This is not an anti-Intel comment. You had a couple of people in the past that had a manufacturing advantage. So it was very, very hard for somebody to come in and compete there. But now, there's sort of equal access to everybody with a big enough checkbook to get great manufacturing, right? So now you have to do something else. And so architectural innovation is a real area we're seeing a renaissance there. A lot of it's machine learning, not all of it, but there's a lot of interesting stuff. And then there's a fabulous opportunity to tell software folks, from the first day of any kind of education onwards, that they're on the front lines of where we go in the future, right? We're going to actually have to write performant software. So I actually think it's fabulously, it's great.
Yeah, maybe that's also something that we can take into our universities when talking about the curricula, that we need to think about the low levels and the cross-layer effects, because software needs to become more efficient now that hardware can't win that much anymore.
Yeah, that's a great way to finish, that we do need to innovate in architecture, and we do need to innovate in our software, and we should educate our future generation to take on that challenge. Like, thank you, Daniel. Thank you, John. It was a pleasure talking to you.
Thank you very much.
The discussion. Oh, you changed room, huh?
Now I'm on a holodeck, you see.
I see.